All right, this video is going to be a review on molarity calculations. The important thing we need to know about molarity is our formula that will allow us to make calculations, and that is capital M, which stands for molarity or concentration. The word is interchangeable. That is going to be equal to the moles of the solute that are dissolved in. Every time I say in or per, I put a divided by sign, and that is going to be liters of solution. When we are looking at story problems, we always have to remember we're always going to be looking for moles to be able to plug into a equation, and we're also going to be looking for liters. So anything that's written in milliliters, we're going to have to change to liters. So here are three problems that we'll deal with molarity. So the first one here, a solution contains 32.7 grams of H3PO4, which is phosphoric acid, in 455 milliliters of solution. Calculate molarity. I try to organize my thoughts ahead of time, so I put my variables on the left side. I say molarity is equal to, moles are equal to, and liters are equal to. And then I go back to my story problem and fill in my blanks. Molarity, you get the question mark because that's what I'm solving for. That's the unknown. Moles. I don't have moles yet, but I have a way to get there. I've got grams, so I'm just going to write a note to myself that I need to calculate the moles. And then liters, I don't really have those, but I basically do. I've got milliliters, which means I just take the decimal point and I move it over 3 to the left, which makes it 0.455 liters. Now I'm going to calculate my moles so I can plug it into my formula. Again, my formula, my master formula is molarity equals moles of the solute divided by the liters of the solution. So my starting point, 32.7 grams of H3PO4. And I'm going to put that into dimensional analysis. Since grams are on top of that first dimension, grams go down here, H3PO4. And we just have to look up on our periodic table what the molar mass of H3PO4 is. So there are 3 hydrogens at 1 gram each, plus 31 grams for phosphorus, plus 16 grams of oxygen, but there's 4 of them, so that's a total of 64, giving us a total of 98.0 grams for our molar mass. And that is the mass of 1 mole of H3PO4. Now we're just going to finish our dimensional analysis by taking 32.7 divided by 98.0. And when we put that into our calculator, we get 0.3367, and whatever. I'm going to stop writing after that. And that's moles of H3PO4. But that's not what we were asking for. We were asking for molarity. So we need to use this number in our calculations to calculate our final answer. So what we will do is we will take those moles and divide it by our volume, our liters. So 0.3367 divided by 0.455 will give us 0.733, and that's the correct amount of significant figures. And we label that molar H3PO4. And that just gets the rectangle because I know that I'm finally done. The next type of problem you might see is how many moles of silver nitrate are needed to prepare 0.50 liters of 4.0 molar silver nitrate solution. This one is actually pretty straightforward. It's, we could put our organization over to our left, moles equals, and liters equals. This time we have our molarity. We'll look for those units to double check that we're writing in the right information. It's 4.0 molar. Moles is our question mark. That's what we're solving for. And our liters this time is 0.50 liters. We don't even have to convert this one to liters from milliliters. So we simply need to manipulate our formula up here at the top to solve for moles. Moles would be molarity times liters when I manipulate that formula algebraically. So I really just have to take my molarity, 4.0, times my volume of liters, which is 0.50. Whoa, 50. That's the ugliest 5 ever. Which will give me an answer of 2, but I need correct amount of significant figures. I need 2 significant figures, so that is 2.0 moles of silver nitrate. And that one will get the rectangle. Whew, that one was pretty straightforward. All right. The third question here says what mass? Okay, that should be the red flag if anything is asking for a mass. We need to get moles first, and moles is our go-between. So we'll use our information and the molarity equation to solve for moles in this instance. So organize our thoughts. Molarity equals, moles equals, and liters equals. We have our molarity at 0.10. We have our liters, and they are in liters, so we don't have to convert anything. Moles is what we're looking for so we can solve our problem, which is mass. So again, we're going to use, just as we did in this problem up here, we're going to use moles is equal to molarity times liters. When I multiply 0.1 times 2.5, I get a value of 0.25 moles of sodium hydroxide. I'm not done. I need to convert that to mass. So I can start some fresh dimensional analysis down here. 0.25 moles of sodium hydroxide. Put that into dimensional analysis so I can convert it to grams. Moles of sodium hydroxide is up on top of this dimension. It means in this bottom dimension, I need to put 1 mole of NaOH. And on the top part of this dimension, I need to figure out the molar mass of sodium hydroxide. Sodium is 23 grams, oxygen 16, hydrogen is 1. Gives me a grand total of 40.0 grams of NaOH per mole. When I multiply and finish my dimensional analysis out, I get 0.25 times 40, which is 10. But I need the correct amount of significant figures. Looks like I am limited by 2, which means my answer must have 2. So I'm going to put a decimal point after that, and that'll be 10 grams of sodium hydroxide are in that solution. Okay, this is another molarity problem we might see, but this one is going to involve stoichiometry as well. So the problem asks us an excess of aluminum is added to 100 milliliters of 0.250 molar hydrochloric acid solution, HCl. What mass of aluminum chloride is formed? All right, so the first order of business on this one is to write out the equation. Many times we will give you the chemical equation, or the chemical equation will be given to you. But if we just read this out, we can find out that aluminum is added to hydrochloric acid. That single displacement reaction will form, just like the problem says, aluminum chloride. Aluminum has a +3 charge, which means our chloride will need 3 of those to balance that thing out. What else is produced? Some hydrogen gas. And now we just need to balance this equation. I can tell that my chlorines are going to be a mess if I just try to put 3 chlorines on the right. It's not going to work out. Take my word for it. I'm going to need 2 of those things, which is going to give me 2 aluminum. It's going to give me 6 chlorines. So I'm going to make 6 chlorines on the left, which gives me 6 hydrogens on the left. Now I've got 6 hydrogens on the left. The only thing that's messed up still is my aluminums, but now they're good too. So there's my balanced chemical equation. Now I can finally get to work on the problem itself. So we have to do a molarity problem first before we can deal with anything else. So I am going to just put on the side, organize my thoughts. Molarity equals, moles equals, liters equals. And I'm going to go back to my problem to fill in whatever information I can. I am given milliliters. And notice I only have one significant figure. So my liters is going to be 0.1. That is also one significant figure when I convert that to liters. My molarity is 0.250 molar HCl. That's 3 significant figures. What mass of aluminum chloride? So I think of this as, here's my starting point. Here's what my problem wants to know. So I need to figure out moles, and don't lose sight of what moles you're figuring this out for. I see many students just tell me that they're figuring out moles of aluminum chloride right away. No, all this information is about hydrochloric acid. So we're going to find out how many moles of hydrochloric acid that is. We are going to use the fact that moles is equivalent to molarity times liters. And when we plug that in, 0.250 times 0.1 is going to be equal to 0.0250 moles of HCl. Now we're going to use stoichiometry to solve for grams of aluminum chloride. So I'm going to do a little color change here and start some dimensional analysis. My starting point is 0.0250 moles of HCl. According to my balanced chemical equation, I look at my coefficients to convert moles of what we know to moles of what we're looking for. So there are 6 moles of HCl, and that reaction will produce 2 moles of aluminum chloride. Now I just continue on with my dimensional analysis and solve for grams. 1 mole of aluminum chloride, when I add up the molar mass of aluminum, which is 27, plus chlorine's 35.5, but I need 3 of them. I add all that mess up and I get 133.5 grams according to my periodic table of elements. Now when I do that dimensional analysis, when I solve for that dimensional analysis, I will take 0.250 times 2 times 133.5. I will get that product, and then I will divide that product by 6. And when I do all of that, my calculator will tell me something like 1.1125. But I cannot write that answer because I am limited by my significant figures. So I have to go way back to the beginning of my problem to figure out how many significant figures can I write in that answer. And my answer will come to me right here. There's only one significant figure, which is why I kind of wrote it here as one significant figure, to remind myself that my answer can only have one significant figure. So I need about 1 gram of aluminum chloride. And that is how much will be formed in that reaction.